Welcome to our EDC 5 A-Game Winter Webinar Series, webinar number 2. You'll notice that we have a lot of folks on the screen joining today. We've got 2 speakers to start out the presentation, and then we'll be joined by 5 additional panelists from several state DOTs for the second half of the session. So we'll be seeing a lot of our crew here in the second part. So some quick introductions just at the beginning here. As part of our webinar 2 kickoff, selecting the right tools for the job, establishing the project goal and the path to get there. We appreciate everybody joining us today. We're going to be talking about how to determine which tools in the toolbox apply for a site investigation, some specific nods to geophysical tools, talking about the benefits of well-developed site investigation and programs, and really the thinking component of subsurface investigations, scoping and justifying decisions and weighing risks when perhaps we go beyond the minimum requirements. Today we've got 2 presenters, Jerry DiMaggio from Applied Research Associates and Eric Lohr from the University of Missouri. As I mentioned in the second part, we're going to have a presenter Q&A and a DOT panel discussion where we'll be joined by John Pilipchuk, North Carolina DOT, Crystal Pelham with New Hampshire DOT, Bill Owen with Caltrans, Mark Fish with the Washington State Department of Transportation, and Rich Lamb with the Minnesota DOT. So with that, I will stop the screen share here and introduce our first speaker in a little more detail. Jerry DiMaggio has more than 40 years of experience in civil engineering and heavy construction. He's internationally recognized for his contributions to design, construction, forensic assessment, and dispute resolution and innovation deployment. He serves as a project manager and technical subject matter expert on a diverse suite of projects at ARA. He has provided consulting services on over 1,000 civil, construction, and business-related projects across the world. Jerry's retired from both Federal Highways and TRB and has presented hundreds of seminars and workshops, and we're fortunate to have him speaking with us today. So with that, Jerry, if you're ready to share your screen, we'll start webinar 2.
Okay, good afternoon, everybody. Thank you, Derrick, for that great introduction that we always write for ourselves and then somebody else presents. That's terrific. So my presentation, I believe Eric's as well, will be about 25 minutes. I have about 20 slides in this particular deck. And what you see in slide number 1, numbers of the slides are located in the lower right-hand corner of each slide. I'll be addressing the topics for the 5 bullets that you see here. Some I'll spend a little bit more time on than others as we go through these slides. And Derrick gave a great introduction in terms of what the objectives and goals are for this particular webinar. So let's begin with the benefits of site characterization. And I'll use my cursor as a pointer as appropriate. And some of these are quite obvious and I won't dwell on, like the initial one, accurate characterization of the stratigraphy. And we do that because it has a tremendous impact on project costs, both directly and indirectly. We're interested in the second bullet on reliable estimates for geotechnical design parameters. And the third bullet speaks to an area that's grown in attention, I would say in the last 15 years, the focus on geotechnical hazards. Regional type hazard, of course, would be seismic, but we could have local hazards as well as other regional hazards. Well, let's speak a little bit about the general objectives of a site characterization. And this is one of 2 slides. Some redundancy with the previous slide, but the objectives are very important for any study that you undertake, because if you don't have a defined objective, you won't know success when you achieve success. So as we said before, we're interested in stratigraphy, groundwater conditions, and honestly, we don't do as good a job as we could and should relative to the underground groundwater environment many times. We're interested in suitability And suitability is for the specific objectives and uses of the feature, the geotechnical feature that we're interested in evaluating. I already mentioned hazards, how we're going to cope with hazards, what are the design protocols and the construction means and methods that are associated with that. Continuing on with that theme of objectives, we're interested in location and alignment and the qualitative characterization of the conditions so that we're better informed in terms of location and alignment decisions for all types of infrastructure projects. And we're focused on the highway community because that's kind of where we all live, at least in part. But everything that's being presented in this webinar series, I believe, with no exceptions, is equally applicable really to all types of infrastructure. Could be rail, could be energy projects, could be wind farms, et cetera, et cetera. We're interested in design parameters, and we're interested, and Eric will cover this in a lot of great detail, is the reliable estimates of the relevant design parameters that we're going to be needing for both design and construction. And still today, I find in my practice, we often forget about the concept of constructability and tied to the design parameter bullet. When we select design parameters, we should be fully cognizant that we're selecting those design parameters for two phases of the projects, of course, design and as well as construction. We're also interested in the last bullet, and it's really looking at the condition assessment of geotechnical features. And here we're mentioning specifically transportation features. Now that might be immediately in post-construction. Many of you are aware of the transportation asset management programs that have been underway for more than a decade in the last two highway bills. And there's a continued growing interest in geotechnical assets. The new AASHTO code, just as an example for design and construction of highway tunnels, has a design life of 150 years. Well, that sounds wonderful, but what does that mean? And how do I develop the protocol for evaluation post-construction between the closure of the project in 150 years? Fortunately, I'm not going to be around, and probably most of you won't either. Let's talk a little bit about risk. That's a buzzword that we hear often. Begin with this slide and a subsequent slide providing a little bit of definition. It's an event that's a futuristic event, and that's often forgotten. So it may occur, it may not occur. The occurrence of that event, we often think of risk as a negative connotation, but if we look at risk and we apply it either at a project or a program or at an enterprise or an organizational level, we can also have risks that are positive, and we call those opportunities. So a little tutorial on the basics of risk management, and we look at it at a project level related to cost, schedule, or the maintenance of traffic or the MOT that's required for a particular initiative that we've got to evaluate. Now, even on a relatively small project, you can encounter lots of risk. I worked with Puerto Rico Highway and Transportation Authority now about 5 years ago on a $2.5 million bridge replacement, and the evaluation of the risk assessments on there, several of which were related to geotechnical, amounted to over 70 risks on a $2.5 million bridge replacement project. Well, you can't address all those things, so there's got to be some protocol for evaluating what risk is more important, both the opportunities and the threats. And we do that by a simple product, and that is, first of all, the likelihood that the risk or the event might occur times the impact or the consequences if the risk should occur. And unfortunately for us, and maybe it's fortunate for us, that many of the risks that are attributed on infrastructure projects are directly tied to site and subsurface conditions, and they often result in disputes, claims, arbitration, bench trials, trial by jury, all painful processes for those of you who haven't gone through this. So a little bit more on risk is, how do we manage these risks? I use the Puerto Rico example of the 70 some odd risks on a $2.5 million project. Well, term that really is applied, and it continues to be struggling to be mainstreamed, I would say, by most of the 52 departments of transportation, is risk management. And you can see by this slide, it involves a couple of steps. At 12 o'clock, beginning with identification, the 70 identified risks. The assessment is really what the consequences of they are, and to prioritize them, because you couldn't, regardless of the amount of financial resources that you were provided, you couldn't accommodate, or nor would you want to accommodate and address all the risk. So you're going to prioritize them. You're going to develop an action plan. So many people, I should say here, many people have the opinion that when you develop a risk register, you can pound your chest and yell Yahoo, and that's terrific, and you're all done. That's really just the start of the program. That takes you through identification and assessment. To really be undertaking a risk management program, you have to develop an action plan. That action plan may require some resources because it's intended to be a proactive plan. Remember, all those risks that you assess are futuristic, and you're doing your assessment at a given point in time. So the risk management plan and the risk register are temporal, and they have to be dynamic. So that requires monitoring of that action plan to see how successful. Maybe some risks don't occur, maybe some new risks occur, and then make your adjustments. That's control. All this can be applied to any topic, and of course, our theme topic for today is related to geotechnical site characterization. So just as a quick example, I've taken a risk, and if you read from left to right on the headers here, a brief description of a risk. Those of you who haven't been involved with risk management at either a project or program level, this is a project level. What's the probability of occurrence? Probability, of course, goes from 0 to 100. What's the impact that can be done qualitatively, as it is in this case, or it can be quantitative? Who's the owner of the risk? Now, that owner doesn't necessarily mean that individual or that organization does all the work. That owner should be really at an individual level, and that individual, represented in this case by the agency, would serve as kind of the facilitator, not the person doing all the work. We look for some thresholds. That's the risk trigger. And then, as I mentioned before, we got to have a plan. And you can see, without going into it, we've got three possible strategies that we can evaluate based on the probability of success and the impact of taking on those actions, those strategies, how successful we would be in mitigating the risk or seizing upon the opportunity. So finally, with that little introduction to risk management, there's got to be some type of link, you would think intuitively, between site characterization and risk. And this is kind of a wordy slide. So forgive me as I read the first header bullet here. Improved site characterization generally is going to reduce the threats. Remember, that's only half of the bucket related to risk, associated with design, construction, and operation of transportation infrastructure. And it does so by the three sub-bullets that you see here. Now, I want to not dwell on those three bullets, but I'd like to make a comment on operation. We have a growing number of P3 projects across infrastructure industry. For those of you who haven't been involved with P3 projects, we have a situation where we have basically a franchise that is being awarded to a group of people that are going to design, construct, and operate the facility in conjunction with the owner agency, typically for a period of 30 to as long as 50 years. And then in a system of good repair, in a condition of good repair, excuse me, those facilities will be turned back over to the owner. Now, P3 projects require some extra thinking on behalf of us who are involved with site characterization, because the information that we gather and the utilization of that information not only is affected design construction, but is related to maintenance and preservation activities that have to occur at least during the period of the franchise. So there's a bit of a value proposition with site characterization. And geotechnical specialists, that includes geologists, engineering geologists, and geotechnical engineers, are known for their whining and moaning. Sometimes, some of us, not all of us. So just a quick check in terms of value-added proposition related to begging or asking or requesting or taking hostages for additional site characterization information. And if you just read along with me, because as I mentioned several times, I detest reading bullets to people. So there's two quick questions highlighted in the lower two sub-bullets. And if you answer yes to both of those questions, site characterization scope that you've laid out produces value and is justified. Now, what happens next? What happens next is dependent upon your ability as a good salesperson. And most engineers and scientists are terrible communicators. So if you've got to sell that to a structural engineer, you've got to sell that to a maintenance engineer, a construction engineer, put on your best tie, make sure you take the mustard stain off, and practice what you're going to sell to people so that you can make the value-added proposition that's appropriate. Well, as you all know, there always is a gap for a multitude of reasons between state of art and state of practice. Specifically in this case, just sharing with you a couple of insights related to site characterization and how wide is that chasm. And again, the bullets here. Great advances in instrumentation and techniques for geotechnical monitoring and geotechnical site characterization. They exist, but they've been slowly adopted into mainstream practice. So if you see one of these tools as we go through this second year of the winter webinar program, whoever came up with that term, kudos for them, is we've got to look at not one success story, but we're interested generally within our sphere of influence on adopting these things as appropriate into mainstream practice. As an example, second bullet, several innovative, great publications on the advances that have been made with the cone. Specifically, the bullet is citing the reports that have been done more recently related to evaluation of liquefaction potential. Now, remote sensing, and we're going to hear quite a lot about that in this series, as Derrick and Ben Rivers will speak to, has been used on a limited basis, but to an increasing frequency on transportation projects and improvements in geophysics, which have been with us really since I was in undergraduate school, which was 50 years ago, my goodness. Well, we've made fantastic advances, not only in sensor technology, but also summarization and interpretation technology of historical geophysical methods. But we've also developed, as you might imagine, and you probably know, some of you, other techniques that didn't exist 10 years ago, 20 years ago, certainly 50 years ago. Now, another topic that is growing in interest is the concept of geotechnical data management. You all know we expend hundreds of thousands of dollars, if not millions of dollars, on the collection of subsurface information, squashing of samples, interpretation of soil and rock and geomaterial samples. And then we do that historically on a project basis. And one of the things that we'll talk about is really looking at, as the first step of site characterization, to take an examination of what we're doing relative to looking at existing information. So you see in this slide depicted, I don't know what DOT's laboratory storage facility that is, but I think we have a structural problem I've identified in a couple of those shelves. The point is, it takes a great deal of effort to obtain and look for the project, secure the historical information, and to retrieve it to the point that it's of use on a project. Now, some of you are familiar with a more specific term called DIGS. And DIGS is one of the tools that's been under development for a couple of decades now, and has come into its own, and you'll be hearing more about that as we go along in other presentations. Talk a little bit about trends that help us related to site characterization. Everybody knows what the letters LRFD now stand for. The geotechnical community went there kicking and screaming. First LRFD AASHTO specification written in 1994 But the geotechnical people, I believe today, have drank the Kool-Aid. And one of the beautiful things about reliability-based design, and specifically LRFD, is that the resistance factor can be directly tied to the quality of subsurface investigation and site characterization. And in current AASHTO Bridge Design Specifications 2020, that's 9th edition, if you've not gotten the latest edition, you see two sub-bullets here that give you guidance relative to the variability and your certainty associated with the subsurface conditions related to the selection of the appropriate resistance factor. Excuse me. Now, just hit on not all of these topics, but I'll make a point here. On this slide is, as a review, are different classes of site characterization investigations. Now, some of these are done in series. Others, like a forensic evaluation, is done in isolation. A borough site investigation might be done in isolation. On some projects, we might follow through on 3 or 4 or 5 of the bullets that you see here. Now, what I'd like to share with you is not all of these, but hit on what I mentioned before a little harder, and that's the office study. I was corrected by a good friend of mine. His initials are BR. I wonder who Ben Rivers is. Anyway, because I had this titled about a year ago as desk studies, which is the traditional term. And Ben advised me that a lot of offices don't have desks any longer, and it was more appropriate to use the term office studies. So I too have drank the Kool-Aid. But back to task here. It represents a critical first step in all site characterization programs. I'm preaching to you, if you will. But the point is, of what you see in these 4 bullets is this is an area specifically that we could devote a bit more attention to, going back to that value proposition, because in the past, we'd have wonderful descriptions of the rock. We'd have wonderful descriptions of geology, but it seemed to stop in many occasions by not fully utilizing the information that was available to us. Minimum site investigations, and I'll be wrapping up here in about 5 minutes or so. If we look at the guidance on the collection and the interpretation of existing information, what we need to do before we look at that and develop our value proposition is to have a good idea of what the minimum subsurface requirements are for a project. And you see those listed here. Note that the last bullet in this slide is when we take the step to the identification of the location, numbers, and the types of tests that will be required. Note that this information is taken directly from the AASHTO LRFD specifications. It existed prior to the AASHTO inclusion, but it is in the AASHTO code or the AASHTO specification if you choose. It's only a code if you go to court and you've got to defend it. Also from AASHTO, we have what we think in terms of naturally when we say collection and interpretation of existing data, and those are the bullets that you see here, no big surprise, if you will. Now, these are busy, busy, busy slides. So I want to go back 2 slides for a minute and remind you of what the objective is in minimum subsurface requirements. And I'd like you to dwell on this slide for just a few seconds before I take you to my 3 busy slides and tell you what it's all about. Now, in a number of FHWA publications, we've got tables such as this, and let me orient you. There's a series of 3 slides, and you'll be able to download, and of course, today's presentation is being recorded. So what's the geotechnical issue, or what's the feature? Shallow foundation, a driven pile foundation here. Next column, engineering evaluations. If, for example, you were undertaking a driven pile foundation design, that's your feature, what are the engineering evaluations that might have to be undertaken depending on the conditions? To make those computations and to undertake that design and analysis, you need to perform some analysis and you need some factual data and some interpreted data for those respective analysis. So sticking at the driven pile example, you could see those listed. What type of field testing might be required in order to provide the information that you need to execute your analysis. And you see those listed, no surprises there as well. And finally, at the extreme right column, you see what types of laboratory tests might be appropriate. Of course, the field testing and the laboratory testing are complementary to each other. Now, two other slides of this type, they exist. I'm not going to go through these as I did using the driven pile example, but you see the types of geotechnical features that are addressed: fill walls, reinforced soil slopes, cut walls. And a final slide of this type: drilled shaft foundations or drilled foundations generically, and embankments and embankment foundations. Now, one thing I haven't mentioned that I think is quite important, and I'm biased because I was one of the co-authors of GEC 14, that's quality or assuring quality in geotechnical reporting documents. And we have a number of reports, as the geotechnical specialist on the webinar today know about: field investigation logs, geotechnical data reports, geotechnical design reports, and geotechnical baseline reports. So this document, if you're not familiar with it, I would strongly encourage you to obtain it and review it. It's focused solely on the design type reports, not geotechnical reports or the documentation that is recorded during the construction phase of the project. So you're zealous, you've collected all this information, you evaluated it all, you've written one or more of these type reports. What do you do with it? You put it on the bookcase. No, you don't. You share it, and you're sharing it with the people, depending on the particular project or the program that we're speaking about. All of the folks that you see in this particular umbrella type approach in terms of a particular project or a particular program would have value from that geotechnical information. Excuse me. Final slide, my presentation. Topic that comes up quite often is how do we deal with investigations for projects using alternative contracting methods? If you're not familiar with the term alternative contracting, talking about design build, contractor at risk, CMGC, progressive design build is another half a dozen I can name, which I won't. Common to all of those delivery methods is that the geotechnical program will be done in phases, but by different parties relative to ownership. Now, we often know that geotechnical site investigation is done in phases. That's not unusual, in particular on major projects. The reality is, however, that on these alternative contracting delivery methods, typically, and I use a specific example, on a design build project, an owner or the owner's agent would undertake some phase one investigation. That might go as far as identifying what are the particular strata that are going to be encountered across the site. The contract is let, design build. Question that comes up: the designer, of course, is then responsible to undertake phase two, phase three, phase four of the geotechnical site characterization. What latitude does that designer have in terms of using the information that was provided in the owner's contracting documents? Now, depending on what state you live in, state law will govern, but federal law basically says that the factual information is such that it can be the factual information relied on by that designer and the design build team. The interpretive opinions, even though they were developed by professionals, could be evaluated, but should not be taken verbatim. And I've been involved with at least a half a dozen major litigation projects specifically to this issue. Well, that's all, folks. And with that, I'd like to turn the program back over to my good friend, Derrick.
Thanks, Jerry. Again, appreciate your presentation today. I think that was really a good overview for us. If anybody out in cyberspace watching the webinar live has a question, do feel free to ask that in the Q&A pod, and we'll work to answer those after the presentation. So if you have anything for either Jerry or Eric, or for our DOT presenters in the second half. Would like to take an opportunity now to introduce our next panelist. So that's going to be Eric Lohr. He's an associate professor in the Mechanical and Aerospace Engineering Department at the University of Missouri. Has performed research for agencies such as the National Science Foundation, Missouri DOT, and Federal Highways, as well as for a number of private contractors and companies. Eric's recent research projects include a number of different interesting areas: recycled plastic reinforcement for superficial slope failures, large-scale laboratory and numerical evaluation of reticulated micropile systems for slope stabilization, constitutive models for the behavior of fiber-reinforced soils, asset management principles and geotechnical engineering systems, and reliability-based design of earth slopes and retaining structures, to cover a few. And he's going to be talking to us today about geotechnical site characterization and how and why we can maybe work a little smarter on that. So, Eric.
Thanks, Derrick, and thanks to everybody for being here this afternoon. It's a holiday week, and so it's nice to know there's so many people still interested in attending. The theme of the day really here in my mind, at least as I understand it, is really about planning and scoping. And Jerry certainly addressed that to some extent, but I'm going to dig a little deeper, if you'll pardon the pun. Ben Rivers had asked me to present really about content that's in the most recent version of the GEC5, the Geotechnical Site Characterization Manual, if you will, and specifically about the probability content. I think that's somewhat new, that's in chapters 3 and 11 of that document. I've titled it, "How do we do it smarter?" Because Ben last week in the introductory webinar kind of mentioned the philosophy of moving away from prescriptive requirements for site characterization and really trying to do that smarter. And what I hope today is that what I can present will enable us to do it smarter. And really, in my opinion, I think the probability provides us with the framework to allow us to do site characterization smarter. I am going to focus a little bit here. Jerry did a good job of kind of summarizing all the different things that we do with site characterization. I'm going to focus predominantly on characterization of design parameters, which is just one component of site characterization, and an important component, obviously, but it's just one. Before I get started, I also want to kind of define a little terminology and specifically related to the use of the terms variability and uncertainty. Really, and I think it's important when we do site characterization, we're really addressing uncertainty. That's what we're trying to do. We use the term variability a lot, and I think geotechnical engineers love that term because it's certainly appropriate for most of our problems. But at least when I use the term variability, it's a term that quantifies how much a parameter changes from one point to another. Maybe from one time to another, but we'll neglect that for the time being. And conceptually, at least, it's fixed. The site is as variable as it is, whether we know it or not. And variability is not something that site characterization is going to change, right? We may be able through site characterization to understand the variability better, but the variability is what it is. And so we need to sort of recognize that. I'll distinguish that from the term uncertainty, and that's really what we're trying to do with site characterization is to reduce uncertainties. Uncertainty is about knowledge, how well we know something, and specifically in the context of what I'll talk about today, how well do we know design parameter values? That's what site characterization allows us to do. If we do a relatively limited site investigation, we don't have a lot of knowledge about what it is we're looking for. If we do a more extensive investigation, we can get a lot of knowledge about those parameter values. These two terms are not completely unrelated. How we reduce uncertainty certainly depends on how we can reduce uncertainty certainly depends on the variability of a given site. The last bullet we could probably debate a little bit, but it's certainly my philosophy is in most cases, variability is best addressed through judicious design. And so if we have a really variable site, really variable stratigraphy, we ought to be thinking about designing things that can accommodate that variable stratigraphy. And maybe that includes foundation systems that can be lengthened or shortened, or maybe that includes specific kind of construction phase evaluations or other kinds of things that we might do. Variability is what it is, and so we're oftentimes best addressed that through design and construction. Uncertainty is what we're after through site characterization, and that's where when we do more investigation, we can generally reduce that uncertainty, and we'll try to put the little quantity on that as we go through. So I'll start here with current site characterization requirements, and like Jerry, I'm kind of focused on the transportation community here, but really it goes beyond that, and so the same kinds of things really apply to other jurisdictions as well. Most of our site characterization practices, and Jerry's kind of summarized some of the AASHTO things, we have prescribed minimum requirements. So a certain number of borings, certain spacing of borings, a boring every 200 feet, a boring every 500 feet, et cetera. Sampling every 5 feet and other kinds of things. So we have some minimum requirements that we're required to do by AASHTO provisions. But there's an important caveat, and that caveat is that based on the judgment of the designer or the site characterization specialist, additional investigation should be performed when it's appropriate and when it's needed. And that's where things honestly get a little bit fuzzy. It's not hard to convince somebody to do the minimum investigation needed as required by the AASHTO specifications. Where it becomes more difficult is when one has to do additional investigation. Unfortunately, maybe it's not unfortunately, that investigation in the current state of the AASHTO specifications really dictates whether or not we're going to achieve the reliability that we're targeting when we do design with the AASHTO specification. And so I'll illustrate that a little bit here with some results from a paper that Dan Ding, Bill Lykos, and I wrote about 5 years ago looking at this. And essentially what we were doing with in this paper is we were simulating design and looking at how does site characterization influence the reliability of designs. And so we did this through simulations, which you can argue with, I guess, but I think they're relatively straightforward. And so essentially what we did is we took sites, and we took sites with different characteristics. We did simulated site investigations, so we would randomly sample measurements from a site. We would take those measurements, develop a design, and then we would evaluate how reliable was that design based on what we really know about the site, about the true site condition. And we would do this repeatedly. And so what we would end up with is a collection of designs based on different site investigations and looking at how reliable were those designs. Well, we chose to categorize the reliability into three categories: a red category, a green category, and a yellow category, as you'll see in the graphs. Green obviously was a satisfactory design, and what that really reflected is a design that practically achieved the target reliability. It was as reliable as we wanted it to be. That's obviously the most desirable result. The yellow curves there, the yellow symbols there represent over reliable designs. And so those are designs that are more reliable than we're really targeting from the design specifications. And that's not a horrible thing, right? If we have to choose under reliable or over reliable, we certainly prefer over reliable. But you can also make the argument that an over reliable design is kind of something left on the table. We could potentially, if we could do things a little bit better, save a little bit of money on construction and other kinds of things. The third category is under reliable, and those are cases where, based on the site investigation, the results of the site investigation produced a design that didn't achieve the target reliability. And that doesn't necessarily mean that design is unsafe. It doesn't mean that we have a failure. It just means we're not as reliable as we're trying to be. And so I'll compare and contrast the two graphs there. The one on the left is for a uniform site, not a perfect site. The site has some variability, but what we would consider to be a really nice site for most geotechnical engineers. The results on the right correspond to results for a highly variable site. So a really bad site, a site where the measured design parameters actually vary quite substantially. And it's the contrast between those two that I think is important here. And what you see on the left for the nice uniform site, really, regardless of the number of measurements that we're allowed to collect, there's actually a very small likelihood of us producing a design that doesn't achieve the target reliability. Perhaps if we're doing very few measurements, there is some likelihood, as you'll see here with my pointer, but that number even is relatively small. Turns out that in fact we get that because most of our designs end up being over-reliable, which again is not the optimum solution, but is not the worst solution either. We contrast that on the right and we see something entirely different. What we see is if we have relatively few measurements and something less than 10, we end up with a very high likelihood that our designs are not going to achieve the target reliability. If we get more and more measurements, that likelihood of getting an under-reliable design decreases, and it decreases pretty substantially. And eventually, if we get enough measurements, we can certainly produce a design that is unlikely to be under-reliable. The point, though, here really between these two extremes, the very uniform site and the highly variable site, is this is where our judgment comes into play. How are we supposed to judge whether our site's going to be like on the left or like on the right, or more likely something in the range of conditions that would fall here in the middle? And it's that judgment, I think, that we need to develop. How do we work smarter? How do we do site characterization smarter? In my opinion, it's really about developing this judgment. I would love to give you a nice simple table that said do this many tests for this kind of a site, and that's just not present. And so I will get to that. To me, the important piece about doing calculating statistics about our site characterization is it gives us feedback, and that feedback helps us to develop and improve judgment. And that judgment in turn allows us to develop and work smarter. So obviously that's not a desirable thing when we have variables, highly variable sites. We would like for all of our designs to achieve the target reliability, obviously. The content in the latest version of GEC 5, the guidance that's provided there was really intended to essentially try to reduce that red curve on the previous slide, to sort of produce this where we end up with fewer under-reliable cases. We did that by including a considerable amount of information about probability and reliability, maybe to the consternation of some, but we did that so that we could reduce the likelihood of having that under-reliable case. Simply put, the guidance that's provided there is that all important design parameters, and we can debate what's important, but I think most people have a pretty good perspective on what that is. We need to establish those to have uncertainty, a coefficient of variation of the model. Really, that's what I'll refer to as uncertainty here, less than 0.3. So this really puts a quantity on uncertainty and really a limit on that uncertainty, and that's intended to reduce that red curve on the previous graph. While we would love to have that all the time, we certainly also appreciated that one may not always get that. And so we just added the guidance that said, okay, if you can't establish the model uncertainty to be less than 0.3, if it's greater than 0.3, then rather than selecting the mean value, which is what AASHTO recommends for sort of an adequate site investigation, you ought to select a conservative estimate for the design parameter. And in that way, in those situations, we can also reduce that red curve and reduce the potential for having an under-reliable case. Okay. A highly desirable consequence of this, I think, in my opinion, and really maybe my key message for today is just the act of doing some statistics on our site characterizations, of quantifying the uncertainty to see whether or not we achieve this limit here. That gives us direct and immediate feedback about how good our site characterization is. And to me, that is really highly desirable. We can improve our judgment. We can do this smarter if we start to evaluate things sort of objectively. Historically, we don't get a lot of feedback about our site characterization practices. When we get feedback is when something goes wrong. And certainly there are problems that have occurred because of inadequate site characterization. If that wasn't true, we probably wouldn't even be meeting here today. But there are also times that things go wrong, not because of site characterization, but yet site characterization often is one of the things that fingers get pointed towards when things go wrong. Okay, so how does this sort of look, I guess, this new guidance, and the guidance is, I think, will change a little bit going forward and get even better. So I've drawn here that, in fact, this is not a transportation project, but certainly it could be. A stratigraphy, a profile of different materials at a specific site. A series of borings were conducted to sort of establish that stratigraphy. Establishing stratigraphy here obviously involves some subjectivity. If we, we've got I don't know, 100+ folks on the call here today. If every one of us looked at the same data, we would probably come up with a little bit different stratigraphy. But my guess is it probably wouldn't be too different for most parts. The objective of site characterization, and really the guidance that's provided in GEC 5, is rather than trying to say, okay, the strength at a specific point is this value, what we want to try to do is to establish and characterize this sort of mass of material that forms one of these material layers, right? And so AASHTO in the specifications defines a site, and the site is really an area over which conditions are relatively uniform. And so rather than trying to sort of focus on point-specific values, I think it's useful to try to consider what we do, the boring, sampling, testing, whether that's field tests, whether that's laboratory tests, whatever it might happen to be. When we run a test, it is really just a statistical sample from this mass of material that we're looking at. And we need to try to characterize each of the different masses that we've got. So I'm going to do a little bit of a sleight of hand here. This graph isn't associated with the site that was shown on the previous page, but the concepts certainly apply. This shows interpretation of a site, in this case, uniaxial compressive strengths of rock based on a series of measurements. And if we just started off with the measurements and had no sort of boundaries there and no other information, there's certainly a subjectivity that's involved with trying to stratify these different materials. And again, we might end up with different strata from different people kind of looking at the same data, but that's okay. That's a part of it. The point I want to focus on here is within each of these strata, there is an interpretation. In some cases, it's sort of a linear varying trend through a stratum. In other cases, it's kind of a constant trend through a stratum. That can be done, with judgment. That can be done with regression, if you would like, but certainly should best involves both of those two. The important piece here for each of these stratums is that we've defined this coefficient of variation. We've defined the uncertainty associated with our interpretation. And so you'll see that reflected by these dashed lines that are on either side of the solid line. That's kind of the interpretation. And you'll see that in stratum 1 here, we've got a coefficient of variation of 0.13, well below the threshold of 0.3 that's recommended in the new GEC 5. And so that certainly would be fine. Stratum 2, a COV of 0.08, again, well below. Stratum 3, largely because we don't have very many measurements and because those measurements are kind of quite scattered, we've got a very high coefficient of variation. This is a stratum that would not satisfy that criteria. And the same is true for the lower two strata. Those also are just above the threshold. And so the point really to quantifying these uncertainty is it tells us something about where do we know, where do we have good information, where do we have reliable estimates of parameters, and where are our parameter estimates a little bit more uncertain, and then we can make judgments about them. If we were to go and do this again, we would learn from what we did and looking at these numbers, and we would say, okay, maybe next time I'll try to get more samples from this stratum, or if even if it's another site, we kind of learn from that. And I think that's really the key lesson or a key benefit of doing those is to get that feedback. And as we get that feedback, we'll get better and better at scoping investigations. One might also ask at this point, well, so I've got what I've got, maybe I can go back out and do some more tests, maybe I can't. The recommendations in GEC5 certainly address both of those cases. We could also try to revise our interpretation. We could combine layers and separate layers. We could combine regions within a site, separate regions within a site. Sometimes that will help, sometimes that will not. Again, there's no real hard recommendation in terms of how to do this. The recommendation really is to get that feedback that you can get from quantifying the uncertainty. So I'll moving on here, kind of just actually kind of almost stepping back about how we do this. And so what do we do? What is it? How do we quantify this uncertainty? And I'm going to go through just a couple of simple examples here. And again, we've done these through simulations, and they're documented in this paper that's cited here. But essentially what we're going to do is we're going to consider two different sites, and these are simulated sites. One's a very nice site. Actually, these are real sites with simulated data to reflect the actual real measurements. What I call the Pemiscot site here is the very nice site. The Warrensburg site here is a highly variable site, and the blue symbols represent the populations of available measurements. Well, if we do these simulations where we simulate different site investigations and we look at what that tells us, it's important to remember that the population is the population. The site is the site. That is the variability. Site investigation is not going to do anything about them. What changes when we do different site investigations is how much do we know about that. It changes in the uncertainty. And it's sort of a shift in perspective. Rather than trying to go out and push a tube at a specific location to get the strength at that location, we're now going to be thinking of that pushing the tube as really just taking a statistical sample of this population and trying to infer what we can infer about the population from that sample. It's important to recognize that when we go out and sample, we don't get to pick which of these test results we get, right? We do get to pick the location, but we don't get to pick whether we're getting a low value or a high value or a nice middle value. We just get what we get. And that results in us having imperfect information about the site. And that's obviously the challenge of site investigation. So I'm going to look at three different parameters. The first one here is the mean. Then we'll look at the variability, which is again, fixed, but what we know about the variability or estimate of the variability does change. And then the final one I'll look at is the uncertainty. And so if we take these two sites, and again, the left one is the nice one, the right one is the complicated one, and we just repeatedly do this simulated site investigation, and we calculate the mean value, what do we get? Well, we find on the left that when we do relatively small numbers of measurements, we can actually get mean values that go over a relatively high range, right? So our actual mean of that population is on the order of 600 or 700 PSF here. If we just take 3 samples, we could get a mean that ranged somewhere from about 350 to something that ranged over 1200 PSF, far different than the actual mean. In most cases, we'll get a mean that's pretty close to the middle. And so the green symbols here represent the mean of the means. But as you do these simulations repeatedly, what you find is that for low numbers of measurements is a pretty great uncertainty in what that mean value. And as I do more and more measurements, I get less and less variability in those means. And therefore, I have less and less uncertainty about the mean. If I do the same thing for the highly variable site, not surprisingly, you get a huge range in the mean value. So if I go out, I have a really variable site and I take 3 measurements and I take the mean of those measurements, I'm most likely to get the mean that's actually reflective of the actual site. But there's a chance that I get values that are really, really low, approaching 0 in this case, or really, really high, approaching over 5,000. Even though the actual mean of those measurements is about 700 pounds per square foot. Okay, and so clearly this is the highly variable site problem. It's not just a problem of having variability, it's a problem of really having very little information about what the actual mean is, what the actual strength is when I get very few tests. As I do more and more tests, 2 things happen. One, well, the primary thing that happens is the range of means that I might calculate from my sample, from my statistical sample, reduces dramatically. The mean actually, the average of those means actually stays pretty constant. If I look at variability in the same way, so now what I'm plotting here on the vertical axis of both of these plots is the variability, our estimated variability in those for our site. Again, small numbers of measurements, you get a big range. You really don't know the variability very well. As you get higher and higher number of measurements, those ranges drop off dramatically. And if you do get to do a lot of measurements, you can get a really precise estimate of the variability. Same is true for the highly variable site. It just takes more measurements to be able to characterize that site with a similar value of variability. Note that for both of these plots, they both sort of approach an asymptote, a constant value. That is the variability of the site, right? We don't change the variability of the site with site investigation. We just characterize that variability. The last one I'll show here is about the uncertainty. And so this is the uncertainty in the mean, which is really what we get to affect with our site characterization. We're not changing the variability, we're reducing the uncertainty. And so here you'll see, again, small numbers of measurements, you get both a lot of uncertainty in that uncertainty, as well as you get more and more measurements, though, that uncertainty drops. In both of these cases, these curves are dropping towards 0. And so theoretically, with a very large number of measurements, we can reduce that uncertainty in the mean to near 0. And that's really what site characterization does. Importantly, it's this COV that we calculate and compare to the limit that we showed for GEC5. It's really this COV that tells us how good our site characterization is. Okay, so that kind of just tells you about how the number of measurements affects reliability. The other thing that's important here is how does the measurement type affect reliability? And we've got lots of different tools. We've got different laboratory tests, different sampling methods, different field tests that we can run, all of which really produce different measurements of different reliability. And so in GEC5, we distinguish between what we call a direct measurement and an indirect measurement. And it's a little bit confusing, I think, in many cases, but essentially a direct measurement is an unbiased measurement of the design parameter of interest. It's a test where if we're interested in strength, we're actually measuring strength, or if we're interested in hydraulic conductivity, we're actually measuring hydraulic conductivity. That would be considered to be a direct test. And it's the design parameter of interest, which is the input into whatever design method that we're choosing to use. And so an SPT test, which is certainly would be considered to be an indirect measurement in most cases. If we're trying to use an SPT test to establish what the friction angle of sand is, that would be an indirect use of the SPT test. But if we're using a design method that takes SPT in value as an input, then actually that test would be considered to be a direct measurement. I'll contrast those with indirect measurements, and those are measurements of a quantity that isn't really the design parameter of interest, but it's something that can be transformed or correlated, if you will, to a design parameter of interest. And so I've shown an example here really related again to the strength of rock. I've got on a horizontal axis the point load strength index, which is really an indirect measurement. That's not really measuring strength. That's just an index test. It's not giving a strength directly, but it certainly can be related to uniaxial compressive strength. And so anytime we're using an indirect measurement, we've got to go through some form of a transformation. Oftentimes they're empirical transformations like we've got shown here, but they can in fact be theoretical transformations, although they still involve some uncertainty. The key when we're using an indirect measurement is that now we've introduced an additional source of uncertainty. Even if I get, in this example that I've shown here, even if I have a perfect point load index, if I get to do 1,000 point load index test of a specific rock sample, I'm going to have a very precise estimate of that point load strength index. That doesn't correlate into a precise estimate of uniaxial compressive strength because I've got uncertainty involved with this transformation. And so this happens to be a transformation that's got considerable scatter, got considerable uncertainty. And so in fact, when I'm using an indirect measurement, the best that I can do with those indirect measurements depends on the uncertainty that's present in this transformation. Well, we can improve that in a couple of ways. You'll see that the data that are plotted here are actually from a few different materials. There's symbols there for shales, or symbols for siltstone, symbols for sandstone, and symbols for limestone. If you try to kind of look, and I'll pick the siltstone because I think it's easy to figure out, all the siltstone, it's sort of clustered down here. If I fit a transformation, a different functional relationship between point load index and uniaxial strength just to the data from the siltstone, I would end up with a transformation that involves less uncertainty. And so I can actually develop improved transformations just by narrowing the scope of those transformations, not considering all rock, but just considering individual rock types alone. I can also go an even step further and actually try to do site-specific transformations. And so while a lot of this scatter comes from the fact that not all siltstones are the same, if I'm designing a bridge at a specific site and I've got siltstone, I really only have to worry about that siltstone. And so if I were to go out to this site, I can do a bunch of point load strength index tests because they're relatively quick and relatively inexpensive. Do a few high quality uniaxial strength tests, and then relate for my site a site specific relationship between uniaxial strength and point load strength. That's going to give me a much more reliable transformation and allow me to much more reliably establish my design parameter of interest, which in this example would be the uniaxial strength. That involves some math, and actually we did some work for the Missouri Department of Transportation a number of years ago that really lets you try to do things like this, where you're trying to combine two different sources of data to establish one single strength parameter. Almost done. This is just another example, influence of measurement type. We all kind of know this fundamentally, but we did a study with funding from the Missouri DOT looking at different sampling and testing methods, and really the quality of different sampling and testing methods. And I think it'd be no surprise that different sampling and testing methods produce different levels of variability and uncertainty. And so here we were looking at undrained strength from relatively high quality boring sampling and testing to things that nobody likes, like the pocket penetrometer or the Tor vane device. And as you might expect, the better boring sampling and testing we do, the higher quality boring sampling and testing we do, we get more reliable estimates for those strength parameters, and we can take advantage of that. So last slide here, really the future, and I put question marks here because I think that the future sort of remaining to be written. As I've described it in this presentation so far, really the big benefit to me of considering things probabilistically is really getting feedback on our site characterization that allows us to get smarter and smarter as we go along. Jerry mentioned the issue of selling, and I wholeheartedly agree with Jerry that we sometimes don't do a very good job of selling the value of our site characterization. Well, one of the things that I think can help us, and this is really maybe for the future, is having resistance factors that depend on site characterization. And it's actually implemented at present by the Missouri Department of Transportation really for about the last 10 years. The beauty of having resistance factors that depend on site characterization, and really depending on the reliability of the parameters, is it establishes a quantifiable and apparent value for site characterization. So you can start to really make good value decisions about when more site characterization is appropriate and when it's not. The final thing is it really shifts the perspective. You know, our current perspective is we need to do more site investigation in order to achieve the target reliability, which is certainly true. And I think that's our current situation. If we can develop these right, we can actually shift that responsibility from trying to achieve the target reliability to really trying to optimize the value proposition that Jerry mentioned. And that really, I think, will improve our practice considerably. All right, with that, I am done. I will pass this back over to Derrick.
Okay, thanks, Eric. At this point, I'd like to invite our panelists to turn their cameras on and join us for the second half of today's webinar. We have a number of questions that we're going to be posing to our group. So again, we've got representatives from North Carolina, New Hampshire, California, Washington, and Minnesota DOTs joining us this afternoon. So I think that Jerry and Eric did a really good job of setting the stage to talk about, what we're looking at in terms of site investigations, what our goals should be. And I thought it was very interesting, the idea of distinguishing the ideas of uncertainty and variability as being sort of in two different bins. So maybe as the first question to our team, how do you currently judge how much to do on a project, and when the established minimums in the LRFD and other codes are good enough, and maybe when you feel it's a good idea or maybe even a critical idea to change the scope of work and do more on a project? And maybe we'll start off on the East Coast and work our way west. Any thoughts from New Hampshire or North Carolina to start us out?
There, I could start. John Flipchuck with North Carolina DOT. It depends a lot on the site, but I guess past experience weighs a lot on how much we feel, how comfortable we are with the level of investigation and how much we're bringing into a site. Parts of the coastal plain that are fairly, consistent. Parts of our Piedmont fairly consistent. That it's that 200-foot interval for roadways, borings, SPTs versus something a little more exotic are fine and fairly, I guess, a recipe kind of thing that we use. But as you get into more risk, into more variability, is when we start looking for other tools. So.
I think in New Hampshire, we have a similar approach. I think Jerry had mentioned about contracting methods. And what we find is that when there are alternative methods of contracting, we do tend to address our method of exploration or method of site investigation a little bit differently, with that using probably more of the minimum standards that we would do for the project. But also, I think what we do is when we look at the amount of risk that's involved in the project, and I think what's worked really well for us recently in getting some of the A-GaME technologies implemented into the projects is engaging those different sections of the department, whether it's bridge or highway, and talking about that risk up front in the design phase of the project, and talking to them about what types of engineering judgment is going to have to be made between borings, or if we can't access a certain location for a bridge project, for instance, the opportunities that do exist in deploying some of these technologies that they're not so familiar with, and having those conversations with them, which also has gone a long way with being able to get these implemented on on other projects.
Derrick, you're on mute.
Thanks. Anybody else have thoughts? Okay, well, maybe building on that and the idea that risk considerations in geotechnical projects, are often informed through our experience, regional geology, understanding of the project expectations. Are there any projects that you can recall where you reduced uncertainties using additional methods, or there was a really big benefit to doing it, or maybe a project that maybe didn't go as well as you had hoped it to because you didn't apply some things? I know that people are always interested in case histories. If anybody has anything memorable.
Yeah, can I share my screen? This is Rich Lamb with the Minnesota DOT.
Sure, you should be able to. Little green button.
This is a real quick example here, but so this is a swamp investigation for a project, about an 800 lineal foot long swamp. And we performed 30 cone penetration tests and 1 standard penetration test boring here. And from that standard penetration test boring, we did consolidation lab tests, and we were able to successfully define the limits of the swamp and also design the consolidation and the embankment settlement with the surcharge and wick drains on this one successfully. So, you know, without the use of cone penetration test equipment on this, I don't think we would have the quality or the accuracy of predicting the settlement that we did on this one. So.
Cool. I appreciate you sharing that with us.
So
And Derrick,
so go ahead. I'm sorry. I was just going to say I'm a strong advocate of cone penetration test technology. If anybody hasn't guessed that yet.
and we haven't used, we've used cone quite a bit in the past years, but we're using it more for like dissipation tests and things like that in our coastal areas. Definitely quicker response, easier or quicker to design for long-term settlement, etc. Versus collecting the tubes, bringing to a lab, and all with our standard rigs. The other thing I was going to say, you know, we have in North Carolina, we're fortunate our designers and investigation groups are all pretty much housed in the same office. So there's across the state. So you have connection with different geology across the state with the designers for the foundations. But one of the big dollar items that we have managed to do from time to time are load tests. And we've had some pretty big bang for the buck. Although it did take a lot of conversation to get folks in upper management to understand that, you know, a few $1,000 or tens of thousands of dollars for a load test can save more than $1 million on a bridge and things like that.
Cool.
Derrick, if
So-
I can for a minute, just add something. I think the comments by Rich and John, I think the cone is a good testimonial to the objective of the A-GaME. If one reflects on how long it took the cone to achieve the mainstream acceptance and use that it has today, we're talking about decades. So what the whole objective of A-GaME is to accelerate the speed of mainstream acceptance and deployment as appropriate.
Yeah, thanks, Jerry. Sort of on that thought about acceptance and using alternate technologies, could maybe one of the panelists or more speak to the idea of using different tools or multi-phase investigations or some of these techniques, especially when they aren't explicitly required by manuals and codes? And is it different depending upon maybe whether or not you do in-house investigations versus contracting for service?
I might be able to speak on that. This is Mark Fish from WSDOT. You know, we have a number of geophysical contractors within our state and sort of at our disposal to utilize. And, you know, we have found that at times, you know, using more than one technique is advisable. We seem to get better results or results that can correlate with one another. And, you know, once the contractor, or if it's us in-house, once we're out there, I mean, getting out there, mobilizing and spending time is what is the most cost and time-consuming scenario. So just to add another test, sometimes, you know, you don't even have to pick up your geophones. You can use the same geophones for multiple types of seismic tests. And then if you have a GPR in your trunk, you could go out and do a quick GPR survey too. So the added cost is sort of minimal as compared to just getting somebody out there to do the work.
Cool, those are some great thoughts there. in general, what advice would you maybe offer to organizations that perhaps see the value in the A-game technologies, but maybe are in the early phases of integrating them routinely? Are there any critical steps toward institutionalizing consideration? Helpful hints, Cliff's notes.
I guess I can comment on that too. Managing expectations, I think, is extremely important. And, you know, you have geophysical contractors that are out there that are trying to, you know, they are the experts and they're trying to, you know, sell you different types of services. And then you have project offices that are designing projects that might be expecting certain types of results. And then you have the geotechnical staff that are trying to sort of be the go-between. And it gets difficult to manage everybody's expectations. The amount of money that you might spend on the geophysical type work, you know, if it doesn't quite work out or give you the answer that you were hoping, the project office could be pretty disappointed and say, why did we waste the money? So really trying to be upfront with expectations and what you think you can and can't achieve is very important.
I would agree with what Mark had just said. And I think along with managing the expectations, it's a bit of an effort, I think, on the front end to have those conversations with a lot of the other bureaus that could be involved that can reap the benefits, but also to understand the limitations. And so when they're requesting us to do geophysics, or we start with that conversation, talking about the different techniques that they can use and making sure that they understand which one was chosen and why it was chosen, but then those limitations that do still exist in the information that they get, but also how it does decrease the risk overall, I think is also an important part of the conversation that you're having when you're starting to use these.
Okay.
Yeah, this is Bill Owen. It's Bill Owen from Caltrans, and I think one of the things that we've always had to consider is making sure that we've educated our clients in how to what actual expectations they can achieve from these particular methods. Oftentimes we get called up and we get asked, hey, we want to do something like, let's say, a GPR survey. And then when we get the project objectives, we can actually go back to them and say, well, you know, GPR might not be the tool that you want here, and come up with some other alternatives for them to try to come up with a better game plan on the project that can increase their chances of success. So a lot of it is, in my experience, it's been basically training and experience. And I think that's something that's been documented before. I think NCHRP Synthesis 357 was one that really talked about what the states needed in terms of training and experience to increase their level of comfort with these methods and what they can actually get for them.
Oh, thanks, Bill.
Along those lines, we had a few questions come up in the question answer pod. So I just wanted to follow along with this expectation idea, or setting expectations. There was one comment that says, I know you cannot have one size fits all. I thought geophysics would help in reducing the uncertainty and variability by scanning a site and then select boring locations instead of you know, every 1,000 feet. So where we're talking about subjective or interpreted geophysical methods and setting expectations for those, how do you set those expectations with factual data that you would you know, want to target specific areas and use simultaneously geophysical methods? And that could be for Bill or Mark or anybody.
Yeah, I think I can throw something out there. This is Bill again. A lot of times, if we're doing a geophysical survey like that as a reconnaissance to get an idea of what variability there is on a project to guide the drilling program. A lot of that is just making sure that our clients understand that a lot of times when we're doing these reconnaissance surveys, we're measuring anomalies. We're not necessarily measuring the physical properties of the material, or we may not have a very good handle on what that material might actually be. We just know that we're seeing something different in one location than there is in another. And that's one of the ways that we help to guide the investigation program to figure out which areas are going to be those of most concern and letting the drilling and sampling be focused on those areas.
Yeah, I might add to that. I remember a specific project that I was involved in a year or two ago regarding voids under a couple thousand feet of highway and how that sort of relates to a drilling program. And we went out there first to try to locate the voids with several geophysical methods. And, you know, it was a few thousands of dollars, or $35,000 or so worth of geophysical work. And ultimately, when we came back, you know, we identified, you know, 24 areas where we think there were voids that we should target for drilling. Well, you know, you start looking at that point, it's like, how much was that cost and geophysical work worth it if we're already going to go out there and do 24 borings to try to find these voids? So, you know, that's kind of a lessons learned, let's say, that maybe all this geophysical work doesn't necessarily, it reduce risks or increases certainty, but it doesn't necessarily, you know, make the project office feel real comfortable when you spend a lot of money.
Mm-hmm. And I can add too, this was a much simpler project, but it was several miles of pavement structure investigation. And I guess to help with the folks looking at the bill, it was patiently educating them that in addition to the geophysics, the GPR survey, we did need to do borings. It wasn't necessarily eliminating some of the pavement cores, et cetera, but it gave us a better product so that, well, yeah, we did do coring, but maybe at 1,000-foot interval or more because we had good GPR information. So not the higher risk that Mark was talking about, but it's just one of those things that people, the education of folks that are asking for this information is pretty important too.
Yeah, along those lines, do you have any suggestions on, you know, Jerry mentioned we're not the best communicators, Eric too, and we do have to be better communicators and better advocates for this salespeople. Any suggestions that any of you have for making that pitch and selling smarter investigations? You know, another. Yeah, go ahead.
Just if I could just add, sorry to interrupt you, but I think a theme that has to be said is in a lot of cases, we're spending somebody else's money or they perceive it as their money. So hence the value proposition and the salesmanship and being a good communicator is tantamount. It's like going to your parents and telling them you want $10,000 for a new car. You better have your game plan. It's not our money. It's somebody else's money.
That's an excellent point. Investment pitch.
Yeah. So a couple of questions came in through the Q&A. How many states on the call at the moment use in-house staff to do their geophysical surveys versus contracting to have that done?
I think I can answer that. This is Bill Owen again. Caltrans, we pretty much do the vast majority of our geophysical investigations in-house. So we have a staff that's involved in it, and so we essentially work the entire state for our various projects. We do have contract support for technologies that we don't use or to handle peak loads, but by and large, we do most of it in-house.
And Mark and Rich, you both in-house, right?
We do about 25% of our work in-house and 75% is contracted out.
Okay. And there was another question about utilizing historic information, how you're taking that data and using it to reduce field investigation. Do you typically find that it supplements investigation entirely, partially, none at all, but it helps inform?
For us, it helps in the planning stages of a project, probably more than the actual finished design. If we have nearby foundation investigations, etc. When another project's nearby, it's, you know, we have that information that we could share, being fairly certain of what kind of foundations we're going to be looking at, etc.
Okay, and a couple of comments came in. Wisconsin does in-house geophysical work, uses consultants, and Missouri DOT limited in-house for resistivity and GPR currently, and anything else would be external. We're getting close to the end of our time, but I did want to ask just a couple additional questions. One maybe to Eric here about some of the work. Is there any time when indirect measurements such as those from a CPT maybe could better characterize things like cohesion, undrained shear strength, maybe better than direct tests because you're getting more measurements as opposed to one lab test?
Absolutely, actually, and I usually try to make that clear in the presentation. There's an implication that direct is better and indirect is, or direct is good and indirect is bad, and that's not necessarily true. In fact, I think usually some combination is probably the optimum, just based on my judgment. But absolutely, you can do better with indirect measurements if you have a good transformation. And so, Rich, I think you mentioned for the example that you showed, you did a lot of cone, which you did one boring with sampling and testing, and essentially that allows you to develop kind of a site-specific transformation where you can get a whole lot of measurements to kind of drive down the uncertainty. And if you can reduce that transformation, then you can do it better that way. So the point I think that's to take away is if you're using an indirect measurement, you got to pay attention to the transformation and do what you can to reduce the uncertainty in that transformation. Lydia Brownell, I think in her little video last week, said MoDOT's looking at the cone in KT, trying to reduce that, right? And so that's really what they're kind of addressing.
Okay, thanks. I guess one final question for some quick answers from our panelists. In using some of the A-GaME techniques, who are you finding are, the real proponents and maybe the folks that are kind of enthusiastically supporting it, as opposed to maybe people that are confused and maybe don't like it so much? Do you have some folks that look at the geophysics records and say, well, that's blue or green or red, what's the blow count for that? Or, I just can't handle the squiggly lines, what's the blow count for that? Or other people that's like, this is great, give me more. So maybe I'll start from west to east this time. Mark, Bill, thoughts on that?
Yeah, actually, since we're essentially an internal consultant to our geotechnical design group, we have a mixed bag of clients, some that will use us on a regular basis and some that don't use us at all. Generally, the ones that we've worked with for a number of years, and typically they have a much better grasp of what the geophysical information is actually communicating. And so we tend to work with them quite a bit, but in terms of beyond that, we're essentially, we keep reaching out to other groups and doing continued outreach to continue to educate new staff as they come on board, and reach out to the other maintenance offices and some of the other groups that can utilize these technologies, and just to keep them in the loop that these methods are available for them. So we've actually found we've had some pretty good success in terms of that outreach and communication. So we're pretty pleased with the results so far.
Cool.
Yeah, I'd say pretty much the same thing. It's a varied group of people that we work with. Some are very enthusiastic and really encourage the use of geophysics and want it. And others, you know, they just, it's not quite up to that level, let's say. And it's important to continue to reach out. You know, it's just not me, but the rest of our management or staff or other engineers or geologists that in our group could also offer the suggestions and is taken up. But then it always comes back to managing expectations, costs, time, availability, and so forth. And, you know, that goes back to, can we do things in-house or do we have to contract it out and so forth? But it's sort of a mixed bag. And, you know, the more we progress each year, it seems like the more work we get or the more excited people are about it.
Rich, John, Crystal?
I'll pass.
Okay.
Pass again.
I agree with a lot of what Mark said. I think we have a very similar experience, and like Bill had mentioned, it can be kind of a mixed bag. And I think the best experiences are the ones that you can walk through the client, if you will, with how you decided on that method, and then what to expect, and then what the data looks like, and then how we're going to use it.
Okay. All right. Well, I would like to thank our speakers today, Jerry and Eric, and all of our panelists. It was great. I'm glad that Crystal, John, Rich, Mark, and Bill, you could join us for the discussion session. I think we had a really good conversation this afternoon. So thanks again. I'd also like to thank everybody that was joining us online live for the presentation. And thank you for watching if you're watching this later as part of one of the A-Game recordings. So this is webinar 2 of our winter webinar series. I'd like to invite everybody to join us for webinar 3, which will be next week at the same time. That webinar topic will be contracting and how to assemble your A-Game team. And we have a number of panelists lined up for that, representing design build construction, a state DOT perspective, and then geophysical applications with question and answers to follow. So again, thank you everybody today. Wish everybody a happy and safe Thanksgiving. Thank you for joining us.
Thank you.
Great, thank you.